All right, so today we're going to start sort of a four-section series of sections about trigonometric identities. And our whole goal in these sections are going to be what we call establishing identities. And let me sort of identify for you first what our situation is where we're starting. So we have two functions, f and g, and they are said to be identically equal if f of x equals g of x. And we could put in here for all x. Okay, but that's sort of understood. If I'm going to tell you f of x equals g of x, it means everywhere. Such an equation is referred to as an identity. And the goal over the next four sections is going to be established that an equation is an identity. And in order to do that, we need some of the identities you've seen before, although we haven't called them that. So the first ones are the first ones we're going to talk about, and they're listed are the quotient identities. You guys remember these, right? Tangent sine over cosine, and cotangent is cosine over sine. Reciprocal identities, which we've been using quite a bit, right? In fact, you used them in just the last section. Cotangent is 1 over tangent, secant 1 over cosine, and cosecant 1 over sine. Pythagorean identities, we've used just a touch. We saw them in one section, and when we saw them there, we sort of made the disclaimer that you don't have to do it this way. You can do it with triangles. Do you remember talking about them just a little bit? Well, there's going to be need for them to be actually used without that triangle approach at this point. So sine squared plus cosine squared equals 1 is the one that I always tend to remember because that one's nice and clean. They're both on the same side and whatnot. The other two, I always forget where the addition is. Is the addition with the tangent or is it with the secant and so forth? But these are the three Pythagorean identities. And they're from the Pythagorean theorem. We could establish them with the triangles and all that good stuff, okay? And the last ones, again, we've used them periodically throughout what we've been doing so far. If you have the ones on the left, I've kind of written them on here the way I have on purpose. These right over here are the odd identities. If you'll notice, they all have the flavor that if you have the negative on the inside, you can pull the negative to the outside, right? Sine and tangent do that, and then their reciprocals do that. And then cosine and its reciprocal are considered even identities because the negative on the inside, it doesn't affect the problem at all. It disappears, if you will. It's equivalent to not having the negative in there. And those were even identities. And we talked about these when we talked about graphs too, right? Talked about even versus odd and what that means graphically and so forth, okay? So I'm going to read this verbatim because I want to make sure everybody really understands this. And we've harped on this with our tutors as well in the Success Center, so they should know this. But if they do something that this says you can't do, you need to make sure and tell them, now my teacher said I can't do that, okay? Remind them, because some of them haven't had trig for a while, and they're supposed to know this, and they do know this, but they just might have a memory lapse for a moment, okay? So this is not the same as solving an equation. Techniques such as adding the same value to both sides, multiplying, dividing, canceling things out, you can't do any of those things, okay? They should not be used. Techniques like this infer that you know that both sides are equal already. And that's exactly what we're supposed to be trying to show, is that they are equal. So you can't infer that they're equal so that you can use properties based on that to prove that they're equal. That's circular reasoning. We can't do that, right? It's the same thing that happens whenever I look words up in a dictionary. I don't know if this ever happens to you, but it drives me nuts, right? So I have had Bible studies that do this before where they will define a word and the word that they're trying to define is in the definition. It's not real helpful. Right? You're supposed to be telling me what the word means, but telling me what the word means with the word in the definition is not so good. And that's equivalent to what you're doing in this situation if you try to do these kinds of techniques. So let's kind of talk about some of the different things you can do. I told you a bunch of things you can't do, which is the things you sort of normally might have thought of. So what are the things you are allowed to do? Okay? So the first thing that you should do is that you should learn the fundamental identities. The fundamental identities are those that are listed earlier in these notes, okay? So notice I said no, not memorize. You should know them. You should learn them. You should think about them. Some of them you already know. You do have them memorized. But this should sort of be on the tip of your tongue so that when you see cosecant squared, you think, oh, that's one of those ones, the Pythagorean theorem, and you can find it quickly. Okay, that's what I mean by learn. You need to know when you might sort of see them or be wanting to use them. The second idea is to rewrite the more complicated side. This doesn't always work, but it is one technique. If you've got one side of the equation that looks really complicated, that's a good place to start and see if you can simplify it to the other side. Okay? The third thing, this is my, when in doubt, when I can't figure anything else out, I always do number 3. This is my default. I rewrite everything as sine and cosine. Because everything can be written that way, right? You know how to write tangent as sine and cosine. You know how to write cotangent that way. You know how to write secant and cosecant. You can turn them all into sines and cosines, and then lovely things will sometimes happen. So that's sort of the default when I can't figure out anything else. Number 4 is keep the goal in mind. There's lots of things you can manipulate both sides of the equations to be. But your goal is to make them the same. Okay? I tell this to my children when we're playing games, right? Your goal is to get rid of this stack of cards. I don't care about any other cards you're working with. Your goal is to do this, and you don't want to get sidetracked in your goal. So keep the goal in mind. The goal is to show that both sides are the same. So don't go off on a tangent. I don't mean this kind of tangent, but a tangent in some direction that's not helpful. Okay? And the last item in here is to remember difference of squares. And I put this in here specifically because it's one that sneaks up on you. So let me show you how that is possible. It can sneak up on you. So a difference of squares, for example, if you have 1 minus sine of x, sometimes you'll end up with something like this in the denominator. One thing that is good to remember is that if you multiplied that by 1 plus sine of x, oh, I left out all these, I'm missing one. Are you guys acting like I'm crazy? There's a number 4 missing. This was 5 and there was 6. I'll come back to 4 in just a second, okay? I'm like, I know there's another one I didn't say. We'll get there. Okay, let me finish up the difference of square stuff. What happens when you multiply 1 minus sine times 1 plus sine? You do end up getting 1 minus sine squared. Now, you should sort of have red flags going off unless you already thought about the fact that this happens. But when you actually are multiplying two binomials together, you should be getting a first term, an outside term, an inside term, and a last term, sometimes called foiling. But whenever you have this pattern where these values are the same, right? You've got 1 in sine, I've got 1 in sine, I've got the different signs, that is a plus and a minus in the middle. The inner term and the outer terms cancel, leaving you with the first term squared and the last term squared and a minus between them. And that's actually really nice because does anybody see how else I could write 1 minus sine squared? It's cosine squared. And the reason it is because the Pythagorean identity says that cosine squared plus sine squared equals 1. So this sort of thing sneaks up on you. And when you use it, you don't always think, hey, I could use this fact. So that's one to keep in mind. The one that I skipped inadvertently is the one that says factor. So factoring sometimes happens where you have a common term to both terms that you need to pull out in front. We'll see an example of that. Or when you have a trinomial, we don't see that quite as often, but a trinomial where you factor things differently. Or you might actually have cosine squared, and you need to turn it into 1 minus sine squared and turn it back into 1 minus sine and 1 plus sine. That's a possibility as well. Okay, so I think the best thing to help you see how these works is to show you some of them. So we're going to get going with some of these examples. All right, so some of them are very quick and easy to establish. Others take a little bit of work. And the other issue that I pointed out last time is that there's not one right way of doing things. There's often several different approaches that we could go down independently, and they would all arrive at the correct solution. Okay? So just because you're seeing me do one thing doesn't mean there's not other options. Now, in some situations, there's a very natural option. For instance, on this one, what do you think you might do? Rewrite. Okay, I think you mean cosecant, right? Yes. Okay. So cosecant could be written as 1 over sine of theta.
And rewrite cotangent as cosine over sine theta.
Okay. Notice I didn't do anything between the sides. I can work on both sides simultaneously, but I can't do anything that affects both sides of the expressions. Okay, both expressions at the same time. What can I do on the left-hand side now? Yeah, and I can actually write it then as cosine over sine, correct? Which is how I already rewrote the right-hand side, cosine over sine. And once they match, you're done. That's your goal. Your goal is to get both sides to match. Okay? Yes, Cole.
Could you leave it as cosine over sine is equal to cotangent? Or would you need to change the cotangent?
Well, one thing you could do, let me show you another option, because everybody's seen this already. I'm going to erase for a moment. You could not change the right-hand side at all. And then down here, recognize that this is cotangent. But you need both sides to say identically the same thing to consider yourself officially done. Okay? So we could go from this route as well. It's just one little sort of minor difference at the end, right? But it's the same thing. Okay? All right, this one does not look quite so friendly. It's actually not too bad. What do you see here that sort of should be a red flag to one of those sets of identities? That tangent squared right there, right? That tangent squared on top should red flag you to which identity? Secant squared. It's the Pythagorean ones, right? In fact, if you flip back or you take a look, tangent squared plus 1 actually is secant squared. It's exactly that identity, right? So I can take that first numerator and I can write it as secant squared, and alpha is the angle being used here. Secant squared of alpha over secant of alpha. And what is secant squared of alpha over secant of alpha? It's secant alpha. I get to cancel one of those out, right? And that's exactly what I wanted. Exactly what I wanted to show. So then we're finished. Okay, so some of them are nice and clean. Some of them have very natural approaches. Yeah? Okay. This one's a bit messier, isn't it? I've got secant to the fourth minus secant squared on the left, and I've got tangent to the fourth plus tangent squared on the right. Suggestions, what would you like to try? Factoring sounds like a great idea, because I don't have any identities that have powers of 4 in them, do I? I don't. But because it's both of them are secant on the left and both of them are tangent on the right, I could factor. So what could I factor out of the left-hand side? Secant squared of x. And I would be left with?
Secant squared x minus 1.
Right. And then on the right-hand side, what could I do? Yeah, we could factor out a tangent squared of x. And what would we be left with? Tangent squared of x plus 1. Now what? Yeah, I definitely have some Pythagorean identity possibilities here, right? There's a relationship that I know between tangent squared and secant squared. So the one on the right-hand side is the most common way of seeing it. What is the tangent squared plus 1 equal to? That's secant squared. And if you take a moment and think about your equation, right, the equation actually says tangent squared of x, I don't know if it's theta or whatever, plus 1 equals secant squared. Could you subtract a 1 to the right-hand side of this identity that you know? Sure. And it would say secant squared of x minus 1, and what would it say that it equals? Tangent squared of x, and that's actually what I have right here, right? Secant squared of x minus 1. So secant squared of x minus 1 is tangent squared of x. And these sides are the same now. I know that they're written backwards, but that's a common property that we're okay with, I think, yeah? Yeah. So these are actually equal, and that's my goal, to show that they're the same. And we did. Okay. Ready for the next one? All righty, we've got sine squared times secant squared plus sine squared times cosecant squared, and it equals secant squared. There's definitely a more complicated side here, agreed? So I don't think we really even need to mess with the right-hand side probably at all. It's pretty well condensed, except for the fact that you might perchance want to write it as 1 over cosine squared, I suppose, but there's really not a lot we're going to do on the right-hand side. But the left-hand side's a general mess. So what do you think we could try? What's your suggestion, Michael? Rewrite in sines and cosines. I think that would be a good approach because the right-hand side has only cosine on it, doesn't it? So let's give that a try. So sine squared's already written the way I want it to be written, so I'll just rewrite it. How would I write secant squared in terms of sines and cosines?
1 over cosine.
That is 1 over cosine squared. And then I've got another sine squared here, so I'll just write it sine squared of alpha. How would I write cosecant? 1 over sine squared of alpha. Please make sure as you're working, I'm glad you said that, please make sure as you're working that the angles don't disappear. I mean, we may verbally say sine squared, but we mean sine squared of alpha or theta or whatever the variable is. You need to make sure it's still there, okay? What beautiful things happen next? Yeah, these two right here cancel to what? 1. So make sure you don't cancel them out completely. It's not 0. They cancel to 1. That's really nice. And this becomes sine squared alpha over cosine squared alpha. Oops, I got an x in there by chance over here. Let me fix that. That's an alpha. What is sine squared over cosine squared? Well, you betcha believe it. It's tangent squared. That's really good too, because what is tangent squared plus 1? That's secant squared, which is exactly where we wanted to end up, right? So I'll put my equal signs in. I didn't move the right hand side at all. I didn't change it, but they're all equal to that, and I get to the end, they are the same. Apparently, when I was making these notes, I was really fond of that particular identity between tangent and secant and Pythagoreans, because we think we've seen it 3 times now, haven't we? In 4 examples, that's pretty good. I don't think the next one uses it, so let's see what we got. Number 5. Sine squared of x times 1 plus cotangent plus cosine squared of x times 1 minus tangent x plus cotangent squared of x equals cosecant squared of x. Isn't that wonderful? It's great. But at the very least, you know where to start. You know you're going to be working on the left-hand side, yeah? Because the right-hand side's just simple already. Do you have a suggestion? How would you start? We could distribute. Absolutely a great idea. And as we're distributing, is it okay as we're distributing if I also change things to sines and cosines?
Yeah.
Can we do that at the same time?
Yeah.
Okay. So I'm going to write this. Then we've got sine. Oh, let me not use red. All right. We've got sine squared x times 1, so that's sine squared x. Plus I have sine squared x. And I've got cotangent, but cotangent is what? It's cosine over sine. Tangent is sine over cosine, so this is cosine over sine. Plus, now I've got cosine squared times 1, so that's cosine squared of x, of course. And then minus the cosine squared times tangent. What is tangent? That one's sine over cosine, good. And then we don't want to forget I've got a plus cotangent squared here. And I don't have the space to write it, but it equals what's still equaling on that side, the cosecant squared. Oh, goodness. All right, well, I've got sine squared of x plus. How will this one simplify? What is sine squared of x times cosine over sine simplified to? Sine times cosine. Everybody agree with that? Awesome. Then I've got cosine squared here of x. Now what does cosine squared times sine over cosine simplify to?
Cosine.
Minus cosine sine. Cosine x, sine x. Don't forget the x's. And then I still have the cotangent squared here at the end. All right, what lovely thing happens next? Yeah, the sine x, cosine x, and the cosine x, sine x, one of them's positive, the other one's negative, so those add to 0, don't they?
Mm-hmm.
They're the same as each other, one's positive, one's negative, so those add to 0. So what I really have left now is sine squared of x plus cosine squared of x plus cotangent squared of x equals. Now what?
That's cosine.
Those two equal.
Yeah, they do. Sine squared plus cosine squared, that's 1. And what is 1 plus cotangent squared? That is cosecant squared, which is exactly what we wanted it to be, isn't it? Yes, it is.